So we have seen now this definition of this category. We'll now look into several examples. Obviously, first comes the motivating examples. So we had in our mind the category of sets, for instance. In this case, set 0 is just the set of all sets. Set 1 is the set of all functions. And partial 0, partial 1, the usual domain, codomain of functions. And E and M, the usual identity function and usual composition. Okay. So that gives us the category set. As a similar one, we have the category of groups, where group 0 is the set of all groups, group 1 is the set of all group homomorphisms, and the rest are usual. Similarly, we have the category of topological spaces, the category of rings, and the category. So these are two different. This is the category. This is the category of rings with identity and homomorphisms. Preserving the identity. While this is the category of rings, which may not have an identity and ring homomorphisms. So for instance, the ring of even integers is an object in Rng, but not an object of Ring, because even integers doesn't have an identity. Okay. Also, the morphisms are different in the sense, if we take integers, from integers to integers, the morphisms in Rng and the morphisms in Ring are different. Okay, so let's keep this as an exercise. Show that the morphisms in ring and ring are different. Okay. Alright, I shall be leaving many such exercises which will be the basis of the assignments that follow this video lecture. Okay. So we have the category of coming back, rings with identity or rings without identity. In general, therefore, any kinds of sets with some structure and structure preserving maps. All of these are examples of a category. So now for some other examples. Firstly, let X be a set. And I am trying to give you as the set of objects, I take the set itself. As the set of morphisms, I also take the set itself. And my partial 0 is the identity map. Partial 1 is the identity map, and so also is the E. Okay. Now let us try and see what am I trying to do. Obviously, if I take this, so I have partial 0, partial 1 and E all as my identity objects. So the first equation is satisfied automatically. There is nothing to look for it. So then suppose if I take an xy from X, what is hom xy? So these are morphisms. So z from this x again, such that partial 0 z is x and partial 1 z is y. So it means it is z such that x is equal to z is equal to y. So in other words, it turns out that hom of xy is the singleton x if x is equal to y, and is the empty set if x is not equal to y. So the picture seems to look like this. So if this were the set X, and if I took an object, an element over here, well, these are the objects. There is only one morphism, and remember, when x is equal to y, this single x is actually my E of x. Okay, so there is only one morphism here, and that's the picture. Nothing connecting them. Okay, so therefore what will be, let's see, if this is the picture, so what will be my composable morphisms? So this will be x pairs from x cross x such that partial 0 x is equal to partial 1 of y, so which is the same thing as, so this means x is equal to y, so is that partial 0 x is my x, this is equal to y, so this means it is this subset, and this is obviously in bijective correspondence with the set X itself. So I take the composable morphisms also to be X. P0 is also then the identity. So this is also equal to P0, P1, and my M. Okay. So of this one should be, as I said, it is already given. So just in line with my diagram. So I 1, 2, 3, 4, 5, 6. So that's the category. Okay. So what is the picture? The picture is, the moment I take a set X, I can make its elements, I can make this, consider the set X as a category whose objects are the elements and morphisms are nothing else but the identity maps. Okay. So this gives rise to something called a discrete category. A category A is said to be discrete if and only if for any two objects Hom AB is non-empty if and only if A is equal to B and Hom AA is nothing else but the identity. Alright? So it turns out that every discrete category, every set gives rise to a discrete category, and the set of its objects of that is nothing else but that set. Therefore, if I start off with a discrete category, this tells me its picture is exactly like this. So, I show that the discrete category are precisely given by sets. So in what do I mean by this? I'll make this, this is a very, very loose statement. What I mean by this statement, what will you have to show, is given a set, as I have shown, I can produce a discrete category. Conversely, given a discrete category, I can produce a set whose discrete category as produced in this construction is nothing else but the given discrete category. Okay, so you go and come back as if. Let's see another example. So this was in which, in some sense, the morphisms were trivial. Now let's make the objects said to be trivial. So let X be a set again. And we now take the set of objects to be singleton. It has only one object. and I take my set of morphisms to be that set X. Now, from any set X to the singleton, that obviously exists one and only one map. So the map partial 0, the domain and the codomain are exactly same. So and I have this map. I say E star is, say, let me put some, let me say, let it put it to be, say, U. It's an element. Okay. Now, obviously, partial 0 E is equal to partial 1. There's no question about it. Now, so what's the picture like? The picture seems to be suggesting is I have this single object and the morphisms are something like this. And there is a very, very special morphism, as I said, this U. So therefore, for X and Y in X, so what is the composable pairs? Therefore, the set of all, every pair is composable, and the projections are the usual product projections, and there exists a M. So therefore, M is a binary operation. Is a binary operation. On X. Further, U is the identity. That means X U is equal to X implies U is the identity. And the associativity then says the binary operation is associative. So it's an associative binary operation with an identity, and hence X is a monoid. Okay? Hence X is a monoid. So if conversely, suppose I have a one object category, then the picture is exactly like this. So one object category makes X a monoid, and so conversely, if I have a monoid, I can make it into a one object category as described. So that's also the third exercise.